In this module, you will learn about different types of relations and their properties. Let's take a quick look at relations that you learned in your previous class. A relation R from a non-empty set A to another non-empty set B is a subset of the Cartesian product of A and B. The subset R is derived by describing a relationship between the first element and the second element of the ordered pairs in A cross B. Let us see an example to make our concept stronger. Here, we have to find a relation R from A to B such that for any A in A and B in B, A is a factor of B and also A is less than B. That is, in the given sets A and B, we have to find the set of ordered pairs A, B such that A is a factor of B and A is less than B. Let 2 and 4 be any arbitrary elements of sets A and B, respectively. Now, 2 is a factor of 4 and also 2 is less than 4. So, 2, 4 is one such ordered pair that satisfies relation R. Likewise, other such ordered pairs can be obtained. Thus, the set of all the ordered pairs so formed is the relation R, which is as shown. The set of all the first elements of the ordered pairs in a relation R from a set A to a set B is called the domain of the relation R, and the set of all the second elements of the ordered pairs is called the range of R. If the ordered pair A, B belongs to set R, then we say that A is related to B, which is denoted by ARB. You also learned that if the number of elements in set A is P, and the number of elements in set B is Q, then the total number of elements in the Cartesian product of A and B is PQ, and the total number of possible relations from set A to set B is 2 raised to the power of PQ. Let us now learn about the different types of relations. Consider set A with elements 1, 2, 3 and 4. The Cartesian product of A with itself consists of 16 ordered pairs, as shown here. Let us define a relation R on A, defined as the set of all ordered pairs x, y, such that x plus y is equal to 15. Recall that any relation R in A is a subset of A cross A. In this case, no ordered pair satisfies the condition that the sum of their elements is 15. Hence, relation R has no ordered pairs in it. These types of relations are known as empty relations. Mathematically, a relation R in a set A is called an empty relation if no element of A is related to any element of A. That is, R is an empty set and is a subset of A cross A. Proceeding further, let us define a relation R in A as the set of ordered pairs x, y, such that x plus y is less than or equal to 8. Choose any arbitrary ordered pair from A cross A. Observe that the sum of its elements is less than or equal to 8. Here, all the ordered pairs satisfy the condition that the sum of their elements is less than or equal to 8. Hence, we get a relation R that has all the ordered pairs present in A cross A. This type of a relation is known as the universal relation or total relation. Mathematically, a relation R in a set A is called a universal relation or total relation if every element of A is related to every element of A. That is, R is equal to A cross A. An empty relation and the universal relation are sometimes called trivial relations. There are 4 different types of relations. Let's first see when a relation is said to be reflexive. Let T be the set of all triangles in a plane. Define the relation R in T by the set of ordered pairs T1, T2 such that T1 is similar to T2. If an ordered pair T1, T1 is in set R, then it implies that T1 is similar to itself, which is true, since every triangle is similar to itself. And this holds true for all the triangles in set T. Hence, we can say that every element of set R is related to itself. Such types of relations are called reflexive relations. Mathematically, a relation R in T is said to be reflexive if every element of set R is related to itself. That is, the ordered pair x, x belongs to R for every x in T. Next, let's see when a relation is said to be symmetric. Again, consider the same relation R in T defined by T1, T2 such that T1 is similar to T2. Let T1, T2 be an ordered pair in set R. Then it will imply that T1 is similar to T2. So we can also say T2 is also similar to T1. This implies the ordered pair T2, T1 is also in R. Such relations are called symmetric relations. Mathematically, a relation R in a set T is said to be symmetric if ordered pair x, y belongs to R, implies that ordered pair y, x is also in R for all x and y in T. Let us take one contradictory example. Relation R in the set 1, 2, 3 is not symmetric. This is because the ordered pair 1, 3 belongs to R, but 3, 1 doesn't. Note that it is wrong to say that it is sometimes symmetric or is symmetric as far as 1 and 2 are concerned, since being symmetric is a property of the whole relation. Let us now move on to transitive relations. A relation R in T is said to be transitive if x, y and y, z belongs to R, implies that ordered pair x, z also belongs to set R. Let's check the transitivity of the relation R in T, which is defined by the set of ordered pairs T1, T2, such that T1 is similar to T2. Consider the ordered pairs T1, T2 and T2, T3 in set R. By definition, T1 is similar to T2 and T2 is similar to T3. Now, T2 is similar to both T1 and T3, so this implies that T1 is similar to T3. This in turn implies that the ordered pair T1, T3 belong to set R. Hence, ordered pairs T1, T2 and T2, T3 belong to set R, implies that T1, T3 is also in R. This shows that the relation R in T is transitive. Now, let's come back to relation R in set T. We observed that the relation R in T is reflexive, symmetric and transitive. Such a relation R in T is called an equivalence relation. Mathematically, a relation is said to be equivalence relation if it is reflexive, symmetric, and transitive. In this module, you will learn about different types of functions. Take a look at the diagram. It shows the graphical representation of the function f1 from a to b. On representing the given function in roster form, we obtain a set with 4 ordered pairs. Observe that different elements of set A have correspondence with different elements of set B. That means the images of different elements of set A under F1 are different. We can also say that no 2 ordered pairs have the same second coordinates. Now, take a look at this diagram. In this case also, the images of the distinct elements of set A under F2 are distinct, or no 2 ordered pairs have the same second coordinate. Such types of functions are known as 1-1 functions. Let us define it mathematically now. A function f from a to b is said to be 1-1 if the images of the distinct elements of a under f are distinct. That is, for every x1 and x2 in the domain of f, f of x1 is equal to f of x2 implies that x1 is equal to x2. Or, if f of x1 is not equal to f of x2, then x1 is not equal to x2. A 1-1 function is also known as an injective function, or simply an injection. Further, if a function is not 1-1, then it is known as many-1. For example, function f shown here is not 1-1 as 2 distinct elements, 3 and 4, of set A have the same image, -3 under f. Hence, function f is many-1. Look at functions f and g. To check the functions for injectivity, we consider any 2 different values in the domain of function f and check that their corresponding outputs are different. In the first case, different elements have different images. Therefore, the given function is 1-1. However, in the second case, the image of 9 and 23 is -4. It means that g of 9 and g of 23 is equal to -4. Hence, the function g is not 1-1. Moving forward, let's now show that the function f from R to R, defined by f of x is equal to 2x, is a 1-1 function. Let x1 and x2 be any 2 arbitrary elements from domain R of function f, such that f of x1 is equal to f of x2. Now, f of x is equal to 2x, so f of x1 is equal to f of x2 implies that 2x1 is equal to 2x2. This gives x1 is equal to x2. Hence, for any 2 arbitrary elements x1 and x2 in the domain of f, f of x1 is equal to f of x2 implies x1 is equal to x2. Therefore, function f from R to R is 1-1. This diagram shows the graph of the function f of x is equal to 2x. Given the graph of a function, you can check whether it is 1-to-1 or not with the help of a test known as the horizontal line test. To check the injectivity of the function f of x is equal to 2x, we draw a horizontal line such that it cuts the graph. This line cuts the graph only at one place. Such types of functions are known as 1-1 functions. In this graph also, the horizontal line is intersecting the graph at only one place. Hence, the function is 1-1. In cases where the line cuts the graph of a function at more than one place, the functions are not 1-1. This diagram shows the graph of a function that is not 1-1. Let's now discuss the onto function. Let's begin by considering a function f from a to b, which is shown here. From our previous knowledge, we can find the codomain and domain of the function. The codomain of function f is set B, with the elements 5, 6 and 7, and the range of the function is also the same set. It implies that the range of the function is equal to the codomain of the function. Such functions are known as onto functions. Mathematically, a function f from a set A to a set B is said to be onto if and only if for every element y of B there is an element x in A such that f of x is equal to y. This implies for every y in the codomain there exists at least one x in the domain. So we can say that the range of f is equal to the codomain of f. Hence, f is onto if and only if f of A is equal to B. The other name for an onto function is surjective function or simply surjection. The functions in which two elements are mapped to the same element are also onto, provided there exists a pre-image of every element in the codomain of f. For example, function f from A to B is onto. However, g is not an onto function since the element 4 in the codomain of g does not have any pre-image in the domain. In this module, you will learn about bijective functions. You have learned that a function f from A to B is said to be 1-1 or injective if every element of A is mapped to a unique element of B. That is, no two elements of A are mapped to the same element of B. Here function f satisfies this condition. So we can say that f is 1-1. You have also learned that a function from A to B is said to be an onto or a surjective function if every element of B has at least one pre-image in A. Here, function f satisfies this condition also, and hence it is an onto function. Thus function f from A to B is both 1-1 and onto. Such a function is also known as a bijective function or a bijection. Mathematically, a function f from A to B is a bijection if it is both 1-1 and onto. Consider a finite set X with the elements A, B and C. Let us define a function f from x to x such that it is a 1-1 mapping. Then every element of domain X has its own unique matching element in codomain X. That is, two elements from the domain of F cannot point to a unique member of codomain X. So the range of function f has three elements, a, b, and c. This shows the range and the codomain of the function f are equal. Recall that if the codomain and the range of a function are equal, then the function is onto. Hence, the 1-1 mapping defined from x to x is also an onto mapping. More generally, for a finite set x, a 1-1 function f from x to x is necessarily onto. Also, an onto function f from x to x is necessarily 1-1 for every finite set x. Let's prove it. Consider the same finite set x and let f be an onto mapping from x to x. This implies the range of f is equal to the codomain of f. We have to show that f is 1-1. Let's begin by supposing that f is not 1-to-1. That means two elements from the domain of x are mapped to the same element in the codomain of f. Suppose b and c are mapped to a under f. Now, we are left with one more element, a, in the domain of f that can be mapped to any one of the remaining two elements in the codomain of f. Let a be mapped to b. This shows that the range of the function is not equal to the codomain of f. This is a contradiction to the fact that the range and the codomain of f are equal. Hence, an onto function defined from a finite set to itself is always 1-1. In this module, you will learn about the composition of functions. Suppose you're at a furniture shop and the shopkeeper is giving a discount of 10% on the purchase of furniture exceeding 5,000 rupees. You purchased furniture worth 8,000 rupees from the shop. Can you calculate the discount that you will get on this purchase? A simple and straightforward approach is to first calculate the amount on which the discount is applicable. This you get on subtracting 5,000 rupees from 8,000 rupees, which gives 3,000 rupees. Next, 10% discount is given on this amount. The discount is 300 rupees. Let us now derive a formula to calculate the discount if a purchase of X rupees is made over 5,000 rupees. In the first step, we have to find the amount applicable for the discount. This we get on subtracting 5,000 from X. Let G be a function from R to R, defined by G of X is equal to X minus 5,000. And then, in the second step, we have to find the discount. Let us define a function f from R to R by f of x is equal to 10% of x. This function will help you to find the discount that a customer gets on the amount exceeding 5,000 rupees. By combining functions f and g, the discount on a purchase of over 5,000 rupees can be calculated. This leads to the definition of composition of functions. If f is a function defined from a to b and g is a function defined from b to c, then the composition of f and g is a function defined from a to c, denoted by g circle f, and is equal to g of f of x for all x belonging to a. In the above case, the purchase is of 8,000 rupees. So taking x as 8,000 rupees, the composition of g and f at x is equal to 8,000 is equal to f of g of 8,000. Now, g of x is equal to x minus 5,000. Therefore, g of 8,000 is equal to 3,000. Now, f of x is equal to 10% of x. Therefore, f of 3,000 is equal to 10% of 3,000, which is equal to 300 rupees. This is the discount. Some important points to remember while forming a composition of two functions are: if f is a function defined from a to b, and g is a function defined from b to c, then the composition of f and g is a function defined from a to c. The function g circle f is possible only if the range of the function f is the domain of function g. When g circle f is possible, f circle g may or may not be possible. If both g circle f and f circle g are possible, then they may or may not be equal. Does the composition of two functions f and g in different order affect the result? In other words, does the composition of two functions satisfy commutative law? Let's see. Define functions f and g from R to R such that f of x is equal to 2x and g of x is equal to 3x square. Let's find the composition of functions f and g first, and then g and f. G circle f of x is equal to g of f of x. Substituting the value of f of x, which is equal to 2x, this gives g of 2x. Now, g of x is equal to 3x square. This implies that g of 2x is equal to 3 multiplied by 2x whole square. Hence, the value of g circle f of x is equal to 12x square. Now, let us find the composition of g and f. F circle g of x is equal to f of g of x. Substituting the value of g of x, which is equal to 3x square, this gives f of 3x square. Now, f of x is equal to 2x. This implies f of 3x square is equal to 2 multiplied by 3x square. Hence, the value of f circle g of x is equal to 6x square. Observe that g circle f of x is not equal to f circle g of x. Hence, we can say that two functions g circle f and f circle g are unequal. Hence, we can say, in general, that the composition of functions does not satisfy the commutative property. Let us now prove some important theorems on the composition of functions. If f is a function from a to b and g is a function from b to c, such that both are 1, 1, then the composition of f and g is also 1, 1. Let's recall. When is a function said to be 1, 1? A function f defined from a to b is said to be 1, 1 if the images of distinct elements of a under f are distinct. With the help of this result, let us begin the proof. We are given that functions f and g are 1, 1. This implies that for any arbitrary elements x1 and x2 belonging to set A, if we have f of x1 is equal to f of x2, then x1 is equal to x2. Also, g of x1 is equal to g of x2 implies that x1 is equal to x2. To prove that G circle F is 1, 1, we'll show that if the composition of F and G at points x1 and x2 are equal, then x1 is equal to x2. Let us consider that the composition of F and G at points x1 and x2 are equal. By the definition of the composition of functions, G of F of x1 is equal to G of F of x2. From equation 2, this implies F of x1 is equal to F of x2. And from equation 1, this further implies that x1 is equal to x2. Hence, the composition of functions f and g from a to c is 1, 1. Let's now move on to the next theorem. If a function f from a to b and a function g from b to c are onto, then the composition of f and g is also onto. Let us consider an arbitrary element z belonging to set C. Since G is onto, there exists a pre-image y of z under function g such that g of y is equal to z. Let us denote this by equation 1. Also, we are given that f is onto, and hence, for y belonging to set B, there exists an element x belonging to set A such that f of x is equal to y. Denote this by equation 2. Therefore, G circle f of x is equal to G of f of x, which is equal to G of y from equation 2. And G of y is equal to z from equation 1. Thus, corresponding to any arbitrary element z belonging to set C, there exists an element x belonging to set A such that G circle f of x is equal to z. Hence, the composition of f and g is onto. Please note that, in general, if the composition of f and g is 1, 1, then f is 1, 1. Similarly, if the composition of f and g is onto, then g is onto. The composition of functions can be considered for n number of functions, but in this class, we are discussing only for 3 functions. If f is a function defined from x to y, g is a function defined from y to z, and h is a function defined from z to s, then the composition of functions satisfies the associative property. Consider any arbitrary element x of set x. Let's begin with the left-hand side, which is the composition of the function g circle f and h. This is equal to h of g circle f of x. This is further equal to h of g of f of x. Now, let us evaluate the right-hand side, which is the composition of the functions f and h circle g. This is equal to hog of f of x, which is further equal to h of g of f of x. Observe that the right-hand side and the left-hand side yield the same result. Hence, the composition of functions satisfies the associative law. In this module, you will study the inverse of a bijective function. Right from your school days, you learned to find the inverse of real numbers. For example, the additive inverse of 2 is minus 2. The additive inverse of 1 by 2 is minus 1 by 2. The additive inverse of minus 1 is 1, and the additive inverse of minus 1 by 9 is 1 by 9. It is to be noted that, on adding the inverse of a number to it, we get 0, which is the identity of the set of real numbers over addition. Now, let's see if the inverse of functions exists. Let us denote the set of numbers 2, 1 by 2, minus 1, and minus 1 by 9 by A, and the set containing the additive inverse of the elements of set A by B. Define a mapping F from A to B such that F maps the elements of set A to their additive inverses in set B. Observe that F is 1, 1 and onto. Now, let's define a function g from B to A such that it maps the numbers in set B to their additive inverses. That is, g maps the elements of set B back to set A. Such a function g is known as the inverse of f. This discussion leads us to the definition of inverse function. Let f be a function from A to B if for any arbitrary element x belonging to A, we have f of x is equal to y in B. Then the function g from B to A given by g of y is equal to x, where y belongs to B and x belongs to A, is called the inverse function of f. Let's now move on and see when a function is said to be invertible. Let 2 be an arbitrary element in set A. Then g circle f of 2 is equal to 2. In general, g circle f of x is equal to x for all x belonging to set A. This implies g circle f is an identity mapping on A. Let's now see if f circle g is also an identity mapping. Consider any arbitrary element, say minus 2, in set B. Then f circle g of minus 2 is equal to minus 2. Generally, f circle g of x is equal to x for all x belonging to set B. This implies f circle g is also an identity mapping on B. Here the composition of f and g and f is an identity mapping. Such a function f is said to be invertible. Mathematically, a function f from A to B is said to be invertible if there exists a function g from B to A such that g circle f is an identity mapping on A and f circle g is an identity mapping on B. The function g is called the inverse of f and is denoted by f with superscript -1. Let's proceed further and learn to find the inverse of a function with the help of an example. Let P be the set of all y such that y is a natural number and is equal to 3x minus 2. Let's show that a function f from n to p, defined by 3x minus 2, is invertible, and let's also find its inverse. Let's begin by considering an arbitrary element, y, in set P. This implies y is equal to 3x minus 2 by the definition of set P. This further implies that x is equal to y plus 2 whole divided by 3. Let us now define a function g from P to n by g of y is equal to y plus 2 whole divided by 3. Now, G will be the inverse of F if G circle F and F circle G are identity mappings. Let's check it out. Consider any arbitrary element, x, from the set of natural numbers. Then, G circle F of x is equal to G of F of x, which is further equal to G of 3x minus 2. And, by the definition of function g, this is equal to x. This shows G circle F is an identity mapping from N to P. Next, let us consider any arbitrary element, y, from set P. Then, F circle G of y is equal to F of G of y, which is further equal to F of y plus 2 whole divided by 3. And by the definition of function f, this is equal to y. This shows F circle G is an identity mapping from P to P. So, from equations 1 and 2, we can say that f is invertible and g is the inverse of f. Now, let's prove one theorem. Let f and g be two invertible functions from x to y and y to z respectively. Then, the composition of f and g is also invertible. That is, the inverse of the composition of f and g is equal to the composition of the inverse of g and the inverse of f. Let's begin with the proof. We are given that f and g are invertible functions. We have to prove that G circle F is invertible, with G circle F inverse equal to F inverse circle G inverse. To prove G circle F invertible, it is sufficient to prove that the composition of G circle F and F inverse circle G inverse is an identity mapping from x to x, and that the composition of F inverse circle G inverse and G circle F is an identity mapping from Z to Z. Let's begin with the first part. By using the associative law of composition of functions, the composition of G circle F and F inverse circle G inverse can be written as the composition of F and F inverse circle G inverse circle G. Again, using the associative law, the terms inside the curly brackets can be written as the composition of G inverse circle G and F inverse. Now the composition of G and G inverse is an identity mapping from Y to Y. Also, the composition of identity mapping with F inverse is F inverse. So we get F inverse circle F, which is again an identity mapping from X to X. Hence the composition of G circle F and F inverse circle G inverse is an identity mapping from X to X. Similarly, we can prove that the composition of F inverse circle G inverse and G circle F is an identity mapping from Z to Z. From equations 1 and 2, we conclude that the inverse of the composition of F and G is equal to the composition of the inverse of G and F. Hence we can say that the composition of two invertible functions is also invertible. In this module, you will learn about binary operations. In earlier classes, you learned that the solution to almost all mathematical problems involve some arithmetic operations like addition, subtraction, multiplication and division in one way or another. These operations involve two quantities and yield a single quantity. Hence, these are also called binary operations, as binary means two. Binary operations can also be defined in terms of functions. Let A be any arbitrary set. Binary operation star on a set A is a function star from the Cartesian product of A to A. We denote star of A comma B by A star B. Let us consider an example to take a broader view. Let Q denote the set of rational numbers. Let A and B be any two rational numbers. Now, on adding, subtracting and multiplying any two rational numbers, we get another rational number. Hence, the function addition from Q cross Q to Q, defined by plus of A comma B is equal to A plus B, is a binary operation. Similarly, the functions subtraction and multiplication from Q cross Q to Q are also binary operations. Now, the division of two rational numbers may not result in a rational number, as A divided by B is defined only when B is not equal to 0, otherwise it is not defined. It means that division from Q cross Q to Q is not a function, and hence not a binary operation. Therefore, we can conclude that addition, subtraction and multiplication are binary operations on Q, but division is not a binary operation on Q. This result can be extended to the set of real numbers R. Also, do check it out. Consider a finite set A with the elements 5, 6, 7 and 8. Let $$ be a relation from A cross A to A, defined by $$ of A comma B is equal to maximum of A comma B. Here the maximum of any two elements of A also belong to set A. This shows that $$ is a function on A, and hence a binary operation on A. This binary operation can be expressed using the table as shown. Here, we have 4 rows and 4 columns in the operation table, with the ijth entry of the table being the maximum of the ith and the jth elements of set A. Such a table is called an operation table. In other words, when the number of elements in a set A is small, the binary operation $ on set A can be expressed with the help of a table called the operation table. In general, we can say that if A is any finite set with n elements, and star is a binary operation defined on A, then the operation table will have n rows and n columns, with the ijth entry being AI star AJ. Conversely, given an operation table with n rows and n columns, and each entry being an element of the finite set A, A binary operation on A can be defined such that AI star AJ is the entry in the ith row and the jth column of the operation table. The number of binary operations on a set A is equal to the number of elements in set A whole raised to the power of the number of elements in the Cartesian product of A. For example, the number of binary operations on a set with 2 elements is 2 raised to the power of 4, which is equal to 16. This is because the number of elements in the Cartesian product of a set with 2 elements is given by 2 into 2, that is 4. Therefore, we have 2 raised to the power of 4. Let's again go back to set Q of rational numbers. Let A and B be any 2 rational numbers. Now, on adding A and B in any order, the result remains the same. That is, A plus B is always equal to B plus A. This implies that set Q of rational numbers is commutative under addition. Hence, the function addition from Q cross Q to Q, defined by plus of A comma B is equal to A plus B, is a binary operation. This discussion leads us to a definition. A binary operation star on set A is called commutative if x star y is equal to y star x for every x and y belonging to the set A. Hence, the function addition from Q cross Q to Q, defined by plus of A comma B is equal to A plus B, is a commutative binary operation. Similarly, the operation multiplication from Q cross Q to Q is also a commutative binary operation, since A into B is equal to B into A. However, subtraction and division are not commutative binary operations, as A minus B may not be equal to B minus A. And similarly, A upon B may not be equal to B upon A. For example, 1 upon 2 minus 2 upon 3 is not equal to 2 upon 3 minus 1 upon 2. Also, 1 upon 2 divided by 2 upon 3 is not equal to 2 upon 3 divided by 1 upon 2. Now, what if we have to associate 3 elements of a set under a binary operation star? In such situations, 2 cases arise. The first is that we can associate the first 2 terms and then associate the result to the third term. The second case is that we can associate the last 2 terms and then associate the result to the first term. If the result in both the cases is equal, then star is said to be an associative binary operation. In other words, a binary operation star on set A is said to be associative if A star B star of C is equal to A star of B star C for all A, B and C belonging to A. Now, addition and multiplication are associative on set Q of rational numbers. Hence, addition and multiplication are associative binary operations on Q. However, subtraction and division are not associative on the set of rational numbers, and hence are not associative binary operations. Now, let us learn something more interesting. On adding 0 to any rational number a, we get a. Hence, 0 is the identity for the addition operation for the set of rational numbers. If we define a binary operation addition on the set of rational numbers, then 0 is the identity for addition for set Q of rational numbers. Also, on multiplying any rational number a by 1, we get a. Hence, we can say that 1 is the identity for multiplication for the set of rational numbers. Therefore, we can say that 1 is the identity for multiplication on set Q of rational numbers. Mathematically, an identity for a binary operation star on A is an element E in set A such that A star E is equal to E star A is equal to A for all A in set A. Now, what if we get an identity on associating two elements of set A under the operation star? The answer leads us to a definition. Given a binary operation star on A with the identity element E in A, an element A belonging to set A is said to be invertible with respect to the operation star if there exists an element B in A such that A star B is equal to B star A is equal to E, where B is called the inverse of A and is denoted by A raised to the power of minus 1. If we again consider the addition operation on Q, then minus A is the inverse of A for the binary operation plus on Q. This is because A plus of minus A is equal to minus A plus A is equal to 0, which is the identity for the addition operation on Q. Similarly, if we consider the multiplication operation on Q, then 1 upon A is the multiplicative inverse of A for the binary operation into on Q. This is because A into 1 upon A is equal to 1 upon A into A is equal to 1, which is the identity for the multiplication operation on Q.